So, for this next section, you're going to be working on using vectors in applications, and they're typically physics questions. So you'll see things like force, okay, and that's a measurement, and you'll also have some of these like flight with direction problems. So let's go through a few of these. So Han and Chewie are flying the Millennium Falcon at 600 miles per hour at 40 degrees south of west. Write their flight as a vector in component form. So what I always want you to do for these problems is draw a picture. And the reason I want you to draw a picture is because if you just blindly do the math, you might miss what quadrant you're working in, and then everything else could be wrong about the problem. So always, not negotiable, always draw a picture. Okay, it doesn't have to be super accurate, it just needs to be a sketch. So 40 degrees south of west. So you do have to know a little bit about your directions. So California is over here. We live on the west coast. New York is over here. That's on the east coast. Chicago is up here. That's north. Texas is down here. That's south. So you do need to know your directions a little bit. 40 degrees south of west. So that means below. So south means like below, right? So below west. So 40 degrees south of west is going to be right here. Okay, so that's why I want you to draw a picture. You really have to understand like what direction you're working with. So my angle theta is not 40 degrees. 40 degrees south of west is not 40 degrees. 40 degrees south of west is 180 plus 40 degrees. Okay, we always go from due east. That's our standard position, right? Due east is standard position. So if I'm going all the way down to 40 degrees south of west, that is 220 degrees. Okay, so our theta is 220 degrees. All right, and then how does 600 miles per hour work? 600 miles per hour is the magnitude. Okay, so if I let F equal the flight, okay, then the magnitude is equal to 600 miles per hour. Okay, so the magnitude is the speed, and then the direction is 220 degrees. Okay. All right, and then it says write their write their flight as a vector in component form. So component form is x comma y, right? Okay, so I need to know if my magnitude is 600, and I am going at 40 degrees south of west, then what is the x component and what is the y component? So first thing I need to point out is your y component needs to be negative and your x component needs to be negative because we are going backwards and down. So that's going to be a negative x and a negative y. So just make sure that your answer lines up. And then it's actually really simple. If you think about SOHCAHTOA, like think about the SO in SOHCAHTOA. So sine of theta is equal to opposite over hypotenuse, right? That's what we know. Okay, well, sine of theta, you don't need to write this down, by the way. This is like stuff you know. The opposite side of my angle is y, and the hypotenuse is 600. So what does y equal? 600 sine theta. And then same thing for x. Think about the ka in SOHCAHTOA. Cosine of theta is equal to adjacent over hypotenuse. Okay, well then that means cosine of theta is equal to x over 600. So what does 600 equal? I'm sorry, what does x equal? 600 cosine theta. So my xy is going to be 600 cosine of theta, which is 220 degrees. And then my y value is 600 sine of 220 degrees. And then all I have to do is plug that into my calculator, and I'm just going to make sure that these values work. So remember that your x and your y, you should end up with negative numbers. So we're going to make sure that we actually do get negative numbers out of this. So 600 cosine of 220 is negative 459.627. And then the y component is negative 385.673. And then I want you to think about, like, is this reasonable? Well, if we have a hypotenuse of 600, we're going to have some pretty big x's and y's to make up a hypotenuse of 600, right? And since I'm going only 40 degrees south of west, so my x and y are pretty close numerically, because 40 degrees is not going down as much as going backwards, but it is like pretty close to 45. Like 45 degrees would be exactly in the middle, which would mean my x and y are the same number. But since I'm a little bit less than 45 degrees, my x's and y's are slightly different numbers. So they're both close. They're both close to 400, but they are obviously going to be different. So that's the writing a vector in component form. So basically, just remember your SOHCAHTOA with those types of problems. But it's pretty much always, I mean, it is this formula here where like x is magnitude cosine theta and your y is magnitude sine theta. All right, Yoda and Luke are moving a droid. I said Luke, weird. Yoda and Luke are moving a droid. Yoda is pushing the droid with a force of 35 newtons. So this is a measurement of force, newtons, at 58 degrees. And it's okay if you don't actually understand like the real physics of this. We're learning how to apply the math. And then when you take a physics class, you will learn more about the actual physics. But we're just covering the math part. And then when you take science, when you take physics, they will explain to you like what all of this actually means. And then you'll be able to apply the math a lot more simply. So with the horizontal, while Luke is pulling droid with a force of 214 newtons at 43 degrees with the horizontal. What is the magnitude of the force exerted on the droid? Okay, so let's draw pictures. And just draw two different pictures. Draw one for Yoda, draw one for Luke. So we've got Yoda is 35 newtons at 58 degrees with the horizontal. So what does that mean? That just means standard position. So 58 degrees from horizontal is going to be here. So 35 newtons is the magnitude. So the force is the magnitude. And then the direction is going to be 58 degrees. So that's Yoda. And then Luke is pulling the droid with a force of 214 newtons at 43 degrees with the horizontal. So Luke's looks like this. That's going to be 43 degrees, and he's pulling at 214 newtons. Okay? So what is the magnitude of the force exerted on the droid? So you might think like, oh, I'm just going to add magnitudes, but you do have to take into account the angles when you're finding the total magnitude of the force. So what we're going to do is we drew two different pictures, and we're going to write both of these, both Yoda and Luke, in component form. So Yoda is going to be 35. It's the magnitude times cosine theta, just like we learned in the last problem. And then it's going to be magnitude sine theta. Okay, Yoda is little. Apparently he doesn't push very hard. Although never mind. We won't get into the lore of this problem. And then Luke is 214. That's his magnitude at a cosine of 43 degrees. And then it's magnitude sine of 43 degrees. Okay. All right. So that is both in vector component form, but we're trying to figure out what's the magnitude of the force. In other words, and that's going to be like pretty much all of these application problems. A lot of them are just what is the resultant force. So another way of phrasing this would be what is the resultant force? Okay, so resultant, as you know, that's just vector sum. So what we're going to do is we are going to add to get the combined force, because both of them are pushing or pulling on this droid. So we're finding the resultant. We're trying to find the total magnitude of the force. Okay. So again, with these application problems, if you have two different or more forces, and it says like, what's the total force, or what's the resultant force, or what is the magnitude of the force, that just means add your component, add the components. Sorry about that. It's a spam call. Okay. So then what do I plug into my calculator? Well, in order to add your components, I'm going to do the x components. So 35 cosine 58. Let's do this on my calculator. So 35 cosine of 58, parentheses, plus, and then separately. So I'll actually write it down here. 35 cosine 58 plus 214 cosine 48. So that's the x component. And then the y component is 35 sine 58 plus, and there's no way to, like, don't try to simplify these. Just plug it into your calculator. Don't try to like combine the sines and the cosines. Don't try to like add the magnitudes and add the, don't do anything weird. Like, you're just going to have to enter it the way it is. So 35 cosine 58 plus 214 cosine, oh, not cosecant, cosine of 48. I'm sorry, 43. Oh, I almost messed that way up. These are 43s, not 48s. Okay, so 35 cosine 58, 214 cosine 43. When I add those, I get 175.057. And then when I add the sines, sine, okay, just make sure it's entered correctly. Okay, I get 175.629. Does this seem reasonable? It does seem reasonable. The reason that I think this is reasonable is if you think about like graphically vector addition. So I've got like 35 at an angle of 58, and then I've got 214, which is a lot longer, but at only 43 degrees. So I've got like Yoda's force here, I've got Luke's force here. Then the total resultant force is going to be somewhere between 43 and 58. So my resultant force ends up being pretty close. I mean, these two numbers are pretty close. So that means my resultant force is pretty close to an angle of 45 degrees. If I wanted to find theta, I would just do tan inverse of your y divided by your x component, right? Using the TOA, tangent is opposite over adjacent, right? And so I would do tangent is equal to y over x, so tangent inverse of y over x, and then that would give me my theta. I'd not asked to do that in this problem, but you will be asked to in other problems. Find the resultant angle measure. And so again, just do tangent inverse. This is also Katoa stuff. Okay, well, what is the magnitude of the resultant force? Okay, so the magnitude, what is the resultant force? What is the total force? What is the, I spelled magnitude wrong. That's going to be the square root of x squared plus y squared. So what I'm going to do is I am going to plug into my calculator the square root of my x, my resultant, my x squared. Oh, why am I rewriting this? I'm just plugging this into my calculator as my x, and I'm plugging this into my calculator as my y. Now, I already have them in my calculator. So remember that you can use the store feature. So like if you go back up to, I'm assuming you're using graphing calculator, if you go back up to this expression, and then you click the button STO, what it does is it's going to store that number into a variable. So you press STO, it's a button at the bottom left-hand side if you have a TI-83 or an 84. Bottom left-hand side, it says store. You're going to store it and then click alpha, the alpha button, like alphabet, and then click like alpha A. And what that does is it stores it as A. And then I would do the same thing with this expression. I would store it in alpha, and then I would store it as like alpha B. Okay, and so that's what I did. And then what I did was I entered into a third line the square root of alpha A squared plus alpha B squared. And that way I'm not rounding. I'm using exact values because I do want your answers to be correct to the third decimal place. And that is going to be 247.973. And then what is the units here? Well, our magnitudes are in terms of newtons. So that is the total force. So that makes sense because if they're both pushing the droid in the same general direction, then they're going to be, then the combined amount of their forces is going to be larger than each individual. So if you think about like combining 214 and 35, that's going to be close to 247. Now it's not exact because you do have to take into account directions. The direction does matter with resultant forces. That's why we had to use it here, right? But overall, it should be fairly close in this situation. Now, if you had something where like one person is pushing in this direction and another person is pushing in this direction, or if like in tug of war, if one person's pulling in this direction and another person is pulling in this direction, then your resultant will be really close to zero. Like if you think about tug of war, you're not, or like in, if you have like two cars, I don't know like cars, but you have two things pushing on each other. They're not, the center doesn't move very much if the forces are about equal. So if that's why the direction matters, because if they're going in opposite directions, the magnitude ends up being like pretty close to zero. Now, if you're pushing in the exact same direction, you can just add the magnitude. So if I'm pushing at like 5 newtons and Jennifer is pushing at 6 newtons and we're both pushing in the exact same direction, then that would be a total of 11 newtons. That would be my resultant force. So if it's the exact same direction, then you can just add the magnitudes. But when the directions are like even slightly different, you do have to take them into account in your resultant. And then you have to find the magnitude of your resultant vector. Okay. But again, please make sure that you know how to use your calculator. Each calculator is different. So I was just kind of going over the 83, 84s. If you don't understand how to use your calculator for this, come to office hours. Or if you have any questions about these types of problems, come to office hours. Or let me know in some way if you want to email me and say like, hey, my entire group was struggling with this problem or whatever, then I can account for that. I can, post better answer keys or post a video or whatever. But you do have to let me know if you are struggling. So please let me know if you have any questions, and please come to office hours if you need anything. I will continue to have office hours only through the end of the semester. I will not have office hours next year, but for the end of this semester, I will continue to have office hours. So please come if you need anything.